everybody, welcome back to College Algebra. Today we're in section 3.2 and we're going to be talking about synthetic division. So first I'm going to show you how to do synthetic division. It's not hard, you're going to like it. And then I'm going to show you how to use the remainder theorem, and we'll need synthetic division in order to use the remainder theorem. And then I'm going to show you how to determine if a given number is a zero of a polynomial function. So here we go. So first of all, what is synthetic division? Well, it's just an efficient, really pretty quick and easy process for dividing a polynomial by a binomial that's in the form x minus some number that we're going to call here k. Now before I show you how to do synthetic division, I want to show you how to do this process in long division. I don't really need you to be able to do the long division process on your own, so I'm going to go through it kind of quickly, but I do want you to have some representation in your mind of what is really happening when we do synthetic division. What are we achieving? So let me show it to you in long division so that you can see what it's doing, and then from there on we'll just always use synthetic division. Okay, so let's say that we want to divide 3x to the third minus 2x squared minus 150 by x minus 4. Now notice I've put the 0x here as a placeholder. Normally if there's not an x term we wouldn't write anything for the x term, but here just to hold the place of the missing x term I've put 0x. Okay, now you know how the long division process works. Basically, you make a guess as to how many times this will go into this, and you put your guess on the top line. Then you multiply back, subtract, and bring down your next term. So that's what I'm doing here. So my first thing is to say how many times will x go into 3x to the third. Well, I'm going to make a guess that it will go in 3x squared times. Now I multiply back. 3x squared times x minus 4 is going to give me 3x to the third minus 12x squared. Now here's where normally we would subtract. In order to keep us from having problems with our signs, I'm going to avoid the word subtract and instead say change signs and add. So you know that that means the same thing as subtract. So now that I've changed signs, I'm going to add. This first set of terms will add up to 0, and then negative 2x squared plus 12x squared adds up to 10x squared. Then I pull down my next term. Now I'm ready to make another guess. How many times will x go into 10x squared? Well, I'm going to guess that it will go in 10x times. Now I multiply back. I get 10x squared minus 40x. And now I'm ready to subtract, but I'm going to say change signs and add. And that's going to add up to 40x. Pull down the next term, which is the last term. And then I say, how many times will x go into 40x? Well, I'm going to guess that it will go in 40 times. I multiply back, change signs and add, and I get a remainder of 10. Now, I know this is the remainder because there's no x here, so this won't go into 10, and there's nothing left to pull down. So this must be the remainder. And remember back to third grade when you first learned how to divide with long division. What did you do with the remainder? Well, it becomes part of a fraction. So, you know, when you were doing this with just regular whole numbers, you would get a mixed number as your quotient. Here, we're going to take the remainder and put it over our divisor, which is x minus 4. So here's my quotient, and then I'm going to have plus 10 over x minus 4. And here is the final answer to our division problem. Now let me show you what this looks like in synthetic division. So in synthetic division, all we do is take the coefficients of the dividend. So I'm going to write down 3, negative 2, 0, and negative 150. Now it is very important that you put the 0 here, because over here with the long division I actually could have gotten away without having this placeholder and I still would have gotten the right answer because I have all the variable powers here to keep me straight. Over here, notice there are no variables. So once you copy this down, there's nothing to tell you what the powers of x used to be. So I need to be able to count on the fact that if this represents the constant, that this will represent the x term, and this will represent the x squared term, and the x to the third term, and so on. So you can see how if I didn't have the 0, that would throw all of that off. Now in the box, I'm going to put 4. And you're going to say, now why do you put 4? Because we're dividing by x minus 4, but remember we're not putting the variables over here. What needs to go in the box is the number that would make this divisor equal 0. So what x value would make this divisor equal 0? Well, if x were 4, this would equal 0. So 4 is what needs to go in the box. Okay, now we'll talk more about that later, but for now, that's why I put 4 in the box. Okay, now here's what we do in synthetic division. Leave yourself a line, a blank line, because we're going to need to write numbers here. And then under your total line, pull down the first term. Just whatever this is, we pull it down. Now we multiply. 4 times 3 is 12, and that will go here. Now we add. Negative 2 plus 12 is 10. And now we multiply. 4 times 10 is 40, and that goes here. And now we add. 0 plus 40 is 40. And now we multiply 4 times 40, and we get 160. That goes here. And now we add. Negative 150 plus 160 is 10. And notice here are all the coefficients of our quotient, but now everything's been reduced by 1 power. So now we started off with this being the coefficient of the x cubed term. In the quotient, this will now be the coefficient of the x squared term. So what I see here is that this is 3x squared plus 10x plus 40, and then I know this is my remainder, and the remainder always goes over the thing we were dividing by. Now since we had 4 in the box, we know we were dividing by x minus 4. So here's the quotient. Notice it's the same quotient we got here, but we're able to get it with a lot less work. Okay, now at this point you may be saying, well, if we can do this, then why do we even have this? Like, why do we even have that lever? So the reason that we still have this process is that this synthetic division process, which is so much nicer, only works if we're dividing by something that can be written as x minus a number. It would not work, for example, if we wanted to divide by 2x minus a number. So you can't have any coefficient here other than 1. And it also would not work if you needed to divide by anything that's not a binomial. So it wouldn't work if you needed to divide by a trinomial, for example, and you'd have to go back to this. But for what we're going to do in this course, we will always be able to use synthetic division. So you will not be required to reproduce this long division process, but I did want you to see it again just so you could see what synthetic division is doing for us. Okay, now just as a reminder, it's really important that if there are any missing terms, any missing powers of your variable, you must put 0 in as a placeholder, because with the variables missing, you won't be able to keep up with the powers unless you know that every power is represented. So for example, if my polynomial that I was dividing into was 4x to the 4th minus 6x squared plus 4, notice that I'm starting with x to the 4th, but I don't have an x to the 3rd term, and I also don't have an x term. So when I write down my coefficients, it's going to need to be 5, 0, negative 6, another 0, and then a 4. So when I look at this, I can know that this is 5x to the 4th, skip the 3rd power, minus 6x squared, skip the x power, plus 4. Now here's the synthetic division process in words. It looks a lot harder than it actually is, but I did want you to have it written down in case that's helpful for you. So we're going to go through this synthetic division process together, and we'll look at the steps as we go. So here's the example we're going to be working with. We're doing 6x cubed plus 10x squared minus 16x minus 8, all divided by x plus 3. So let's follow the steps here. To divide a polynomial p of x, which we have in the top here, by x minus k, which we have in the bottom here. first we need to write all the coefficients of our polynomial in descending order of the variable. If any powers of x are missing, put a 0 where that coefficient should go. So first let's check out if any powers are missing. We have here the third power of x, so the next term should be second power, and it is. The next term should be first power, and it is. And the last term should be the constant. So we're all good to go. We won't need any 0 placeholders. So we're just putting down our coefficients. Now, I know you're already worried about how to show your work in the show work window, and so let me just tell you that the easiest way to do this in MyLabs Plus is to use the text tool, not the math expression tool, and in order to make your little box and your line that goes below here, you're going to need to use the pencil tool or the drawing tool in the show work window, because there's no way in the show work window to type something like that. So just go ahead and use the pencil tool for those things. Okay, now step 2, leave space for a row of numbers under the coefficients and draw a line like the equal line under an addition problem. So make sure and leave yourself a blank row here, and then you can draw that line there. And now you can draw your box to the left of the coefficients, and it says write k in the box. Alright, now remember, we have to be dividing by x minus k, but this says x plus 3. If we think about it in minus form, x plus 3 could actually be written as x minus negative 3. You see that? Because minus negative makes plus. So when we're thinking about x minus k, we need to know that although this says x plus 3, in minus form, it's actually x minus negative 3. So negative 3 is what goes in the box here. But I will point out to you that remember how we did in the very first example that we looked at, and we said the number that goes in the box is whatever makes this expression equal 0? You can still do that. If you don't want to rewrite it this way, it's easy to just look at this and say, okay, I'm dividing by x plus 3. So what would make this equal 0? Well, negative 3 would make this expression equal 0. So that's what goes in the box. Okay, now pull down the first coefficient. So we pull down our 6. Okay, now multiply by the number in the box and write the answer under the next coefficient. So negative 3 times 6 is negative 18, and that needs to go here. Okay, now add that number to the number above. 10 plus negative 18 is negative 8. Continue multiplying and adding until you run out of numbers. Okay, so now multiply. Negative 3 times negative 8, that's positive 24. Now add. Negative 16 plus 24 is 8. Now multiply. Negative 3 times 8 is negative 24, that goes here. And now add. Negative 8 plus negative 24 is negative 32. Okay, now remember, this represents your quotient. The bottom row forms the coefficients of your quotient. The power will be one less than you started with. The last number is the remainder. Okay, so we started with x to the third. Therefore, this must represent the x squared term. So our quotient is 6x squared minus 8x plus 8 minus 32 over what we divided by. Now, what did we divide by? Not negative 3, but we divided by x plus 3. So we put minus 32 over x plus 3. And that is the synthetic division process. Okay, now let's practice with this process. So if you would like to pause the video here and try this on your own, I would totally encourage you to do that. And if you've had a chance to do that, now I'm going to go through this with you. So if I'm going to use synthetic division to do this, the first thing I do is look at my terms and see if I'm going to need any 0 placeholders. So here I'm starting with the x to the third term, then I have x squared, then x, and then the constant. So I don't need any placeholders, and I'm just going to copy down my coefficients. 5, negative 6, negative 28, and negative 2. Now we need to decide what goes in the box here, and we're dividing by x plus 2. So what is the x value that makes this bottom expression add up to 0? Well, if x plus 2 equals 0, then x must be negative 2, so that is what needs to go in the box. Now leave a blank row and draw your line below that and pull down the first coefficient. Okay, now we multiply, add until we reach the end. So negative 2 times 5 is negative 10. Now add negative 6 plus negative 10 is negative 16. Now multiply negative 2 times negative 16, that's positive 32. Now add negative 28 plus 32 is 4. Now multiply negative 2 times 4, that's negative 8. Now add negative 2 plus negative 8 is negative 10. And here is our quotient, but it's in code. See, we have to know what power of the variable this first term represents. So if we look at what we were dividing into, we started with the x to the third term. So we know that this quotient, the first term represents the x squared term. So our quotient is going to be 5x squared minus 16x plus 4 minus 10 over our divisor. So minus 10 over x plus 2. And there is our quotient. Now, what are we going to do with this synthetic division process that we now have? Well, one of the things we're going to do is develop what's called the remainder theorem. Now, before I just dump that on you, let's kind of work up to it. So I want to remind you what you learned about checking division in elementary school. So let's just look at a basic division problem. Here is 348 divided by 7. So no variables, no polynomials, just regular whole numbers. And if we do this by long division, then I can say 7 will go into 34 4 times, multiply back and subtract, then pull down. 7 will go into 68, 9 times, multiply back and pull down, and our remainder is 5. So 348 divided by 7 is 49 and 5/7. Now, if you can remember back to 3rd or 4th grade, after you learned this process, your teacher showed you how you could check your division. And she probably said to you something like this: in order to check that your quotient is correct, you should be able to get the dividend back by taking your quotient and multiplying by the divisor, and then adding the remainder back to that. And sure enough, if we do 49 times 7, we get 343, and then that number plus 5 is 349. So it does work. So notice that in division form it looks like this, but we also can write the same fact in multiplication form like this. The number we divided into is equal to the quotient times the divisor plus the remainder. So we can do a similar thing with polynomials. Let's take this one from example 1. We've already done the synthetic division here. So we know that 5x to the third minus 6x squared minus 28x minus 2, all divided by x plus 2, gives us 5x squared minus 16x plus 4 minus 10 over x plus 2. Okay, now using the same logic that we used over here, in multiplication form, we should be able to say that this polynomial that we divided into is equal to our quotient times our divisor, so see that, plus the remainder, which the remainder was negative 10, so I'm just going to write minus 10 here. Now, I'm not going to take the time to do it, but if you did multiply this back together and then subtract 10, you'd see that it would all add up to this original polynomial that we divided into. And this leads us to the remainder theorem. We're almost there. Now, just like we did in example 1, any polynomial can be divided by a binomial of degree 1, and the result will always be a quotient polynomial and a remainder. In other words, you can take any polynomial, divide by x minus something, and you'll always get a quotient polynomial and a remainder that you can put over that divisor. In multiplication form, we can write it this way. The polynomial we started with should be equal to the quotient times the divisor plus the remainder. That's exactly what we saw in the last slide. Now think about this. Here's where this fact gets turned into something useful. If we want to evaluate p of x at some number that, let's call it k, then we would do that by plugging in k, right? And you would just plug k into your polynomial and multiply each term and then add all the terms together and you'd get your answer. Well, the remainder theorem says that instead of doing that, now we have our polynomial written in this form. So we can plug k into this form. And look what happens here. Instead of working out p of k for ourselves, now we have q of k times k minus k plus r. Now look at this right here. K minus k is going to be 0. And that means that q of k times 0 is also going to be 0. That's huge. So that means that p of k is just equal to r, because all of this becomes 0. And so here's the remainder theorem. P of k is the remainder that you get when you do p of x divided by x minus k. So basically what we have here is another, sometimes more convenient way of evaluating a polynomial. Instead of plugging in the number and doing all the multiplying and adding ourselves, we can get away with just doing an easy synthetic division process, and the remainder is equal to p of k. Let's check it out. Again, here's the remainder theorem. Any polynomial f of x can be evaluated at k if we work out the division f of x divided by x minus k. Whatever you get for the remainder is going to be f of k. So remember back from example 1, this was the problem that we worked, and we found out that the quotient was 5x squared minus 16x plus 4 with a remainder of negative 10. Remember that? Well, now, just as a test, let's evaluate f of negative 2. So we'll do it the old-fashioned way. We're going to plug negative 2 in here. I just want you to see that the result we will get is equal to the remainder we got from our synthetic division process. So plugging in negative 2, I'm going to have 5 times negative 2 to the third minus 6 times negative 2 squared minus 28 times negative 2 minus 2. Okay, now we go back and evaluate each of these powers. Negative 2 to the third is negative 8. So we have 5 times negative 8. Negative 2 to the second is positive 4. So we have negative 6 times 4. And then there are no more exponents, so I'll just go ahead and do this multiplication. Negative 28 times negative 2 is positive 56, and then we still have our minus 2. Now let's do these multiplications. 5 times negative 8 is negative 40. Then negative 6 times 4 is negative 24. Copy the rest. And then if you add all this up, negative 40 minus 24 is negative 64. Negative 64 plus 56 is negative 8. And then negative 8 minus 2 is negative 10. So you see the result of plugging in negative 2 was the same as the remainder we got from the synthetic division process. And I think you'll agree with me that getting that remainder from the synthetic division process was a lot less work than we had to do here. See, here we have to keep up with sign rules and all these powers, and then we have to add correctly. And this can be a little bit of a tedious process, but a lot of times the synthetic division process is not so tedious. So whenever we can from here out, instead of evaluating by plugging in, we'll always evaluate by using the remainder theorem. So now let's practice using the remainder theorem here in example 2. It says, let f of x equal negative x to the fourth plus 3x squared minus 4x minus 5. Use the remainder theorem to find f of negative 3. Now I know that back in chapter 2 you learned how to evaluate functions by plugging in this value. So you know that you could evaluate this by plugging negative 3 in everywhere you have an x. The point here is that we're being asked to use the remainder theorem. So on your quiz, if you are asked to use the remainder theorem to evaluate f of negative 3, and you do that by plugging in negative 3, you're not using the remainder theorem. You will get the right answer, but you're not doing it the right way. So it's very important that you demonstrate on your quiz that you understand the remainder theorem. Do not plug in the value in order to evaluate the function. You must demonstrate the remainder theorem. So the remainder theorem says that f of negative 3 is going to be the remainder of this division. So remember it said you have to divide by x minus this number. Well, x minus negative 3 would be x plus 3. So I've written it here as x plus 3, but it's negative 3 that needs to go in the box. So my coefficients here need to be -1, and then I don't have an x to the third term, so I need a 0, and then a 3 for the x squared term, then a -4, and then a -5. And we're wanting to evaluate f of -3, so -3 goes in the box. Now leave your blank line, and then draw your equals line and pull down the first coefficient, and now multiply. So -3 times -1 is +3. Now add. 0 plus 3 is 3. Now multiply. -3 times 3 is -9. Now add. And we get -6. Now multiply. -3 times -6 is +18. And add. And we get 14. Now -3 times 14 is -42. And add. And we get -47. This is our remainder. So now we know that f of -3 is -47. So we used the remainder theorem. We've shown the synthetic division that has -47 as a remainder. So we know that f of -3 is -47. And this is how you need to show your work on your quiz. Okay, now here's one for you to practice on, and I hope you'll pause the video for a minute and try it on your own. And now I'm going to go through it with you. So this one says, let f of x equal x to the third minus 4x squared plus 2x plus 1. Use the remainder theorem to find f of -1. Now what does the remainder theorem say? The remainder theorem says that f of -1 will be equal to the remainder that you get when you divide this function by x minus -1, which we would actually write as x plus 1 if we wanted to write out the division. So to find this remainder, let's do the synthetic division. So we'll copy down the coefficients. We have 1x to the third minus 4x squared plus 2x plus 1. And now we want to evaluate our function at -1. So -1 goes in the box. Here I've left a blank row and I've drawn my line. So now I'm going to pull down the first coefficient and multiply back. -1 times 1 is -1. Now add, we get -5. Now multiply. -1 times -5, that's +5, and add, we get 7. Now multiply -1 times 7, and that's -7, and now add, and we get -6. So now because -6 is our remainder, we can say that f of -1 equals -6. Okay, now let's move on from the remainder theorem and let's talk about testing potential zeros. So what do I mean by zero? Well, a zero of a function is just a number k such that f of k equals 0. So in other words, the zero of a function is a number that when you plug it into the function, you get 0. If you're looking at a graph, the real number zeros of a function are basically the x-intercepts on the graph, but there could be other zeros that are not real that wouldn't show up on the graph. But the real number zeros are just the x-intercepts. Now, we're going to keep using the remainder theorem because that synthetic division process gives us a quick way to know if a number k is a zero of a polynomial function defined by f of x. So what we're going to do to find out if a given number k is a zero of our function is we're going to use the synthetic division process to evaluate f of k. If the remainder is 0, then that means f of k equals 0, and that means that the number k is called a zero of that polynomial. If the remainder is not 0, then k is not a zero of our function. So it's pretty easy, right? If we do the synthetic division and the remainder is 0, then the number we're working with is a 0. If the remainder is not 0, then the number we're working with is not a 0 of the function. And when we're talking about functions, we talk about the 0 of the function, but a 0 of f of x could also be called a root or a solution of the equation f of x equals 0. So the terms are kind of interchangeable, not exactly, but sort of. So we talk about the 0 of a function, but we could also be talking about the root of an equation or the solution of an equation. Okay, now let's practice with example 3. This says determine whether the given number k is a 0 of f of x. So here's our function. F of x equals x to the third minus 4x squared plus 9x minus 6. and the number k that they gave us is 1. So in other words, they want us to find out if 1 is a 0 of this function. Now, how will we know that? Okay, 1 is a 0 of this function if f of 1 equals 0. That's what it means for a number to be a 0. It means when you plug it in, you get 0. But remember, we're trying to avoid just plugging in. We want to use our remainder theorem. So what we need to do is run the synthetic division with 1 in the box. If we get a remainder of 0, then we'll say yes, 1 is a 0 of this function. If we get a remainder that's not 0, we'll say 1 is not a 0 of this function. So here we go. Our first term is an x to the third term. So our coefficients are 1, -4, 9, -6. Here we have x to the third, x to the second, x, and then the constant. So we didn't need any 0 placeholders. We are trying to evaluate f of 1, so we'll put 1 in the box. Now we are ready to pull down. So we pull down that 1, multiply that. 1 times 1 is 1. Now add. -4 plus 1 is -3. 1 times -3 is -3. Now add. 9 plus -3 is 6. Now multiply that. 1 times 6 is 6. And now add. And we get 0. And because we have a 0 remainder, now we can say that f of 1 equals 0. And since f of 1 equals 0, that means yes, 1 is a 0 of this function. And another way of saying that is to say that 1 is a solution of this function set equal to 0. Now here's part B. And this is one that you could pause the video and try on your own if you want to. Here we have f of x equals x to the fourth plus x squared minus 3x plus 1. And we want to know if -1 is a 0 of this function. So -1 is a 0 of this function only if f of -1 equals 0. So we better be able to do the synthetic division and see that remainder equal to 0. Now be on your guard here because we have a missing x to the third term. Notice the powers go x to the fourth, then x to the second. So we need to put a 0 placeholder, and our coefficients are going to be 1, 0, 1, -3, positive 1. 1, 0, 1, -3, positive 1. We're wanting to find out if -1 is a 0, so -1 is what goes in the box. And now we run the synthetic division. Pull down, multiply, -1 times 1 is -1. Now add, 0 plus -1 is -1. Now multiply, -1 times -1 is positive 1. Now add, now multiply, now add, and then multiply. -1 times -5 is positive 5, and now add. 1 plus 5 is 6. And so here the remainder we got is not a 0. We just found out that f of -1 is equal to 6, not 0, so that means that -1 is not a 0 of f of x. And here in part C, we're going to be doing the same process, but notice this time they gave us a complex number for k. So it's going to be a little more work to do the synthetic division, but we still can do it the same way. We'll just have to be careful when we're working with our complex numbers. You may kind of have to refresh your memory way back to section 1.3 on how we deal with complex numbers, but I'm going to run through it with you here. So we're being asked for the function f of x equals x to the fourth minus 2x to the third plus 4x squared plus 2x minus 5 if 1 plus 2i is a 0. Well, 1 plus 2i is a 0 of this function if f of 1 plus 2i equals 0. Now, see, here's a place where you really would not want to have to plug in 1 plus 2i, because there is nobody in the world who wants to try to work out 1 plus 2i to the fourth power or 1 plus 2i to the third power, because that would just be a real pain in the neck. But the synthetic division process is really going to help us here, because although it's going to be harder than it was on the real number problems, it's still easier than trying to plug in the complex number. So let's go ahead and write down our coefficients. And this time, because we're working with a complex number in the box, let's space them out. Give yourself plenty of room, because our work is going to need to be wider here. Okay, so it's going to be 1 x to the fourth, and then minus 2 for the x to the third coefficient, and then 4, then 2, then negative 5. And I've left myself a little extra space here. In the box, we have 1 plus 2i because that's the number we're working with. Okay, now to do the synthetic division, pull down. Now multiply. 1 plus 2i times 1 is still just 1 plus 2i, so that wasn't hard. Now we add. Remember, when you're adding complex numbers, you add real part to real part and imaginary to imaginary. So negative 2 plus 1 is negative 1. But then the imaginary part here is 0, so 0 plus 2i is 2i. And now we're ready to multiply. Here's where you have to be careful, because you can't do this multiplication mentally. You'll need to come over here and do it. And because you can't do it mentally, you really, if you're asked to show your work on a quiz, you need to type out this part because it's part of your work. So we're going to be multiplying 1 plus 2i times negative 1 plus 2i. Let me do that right here. So this is the FOIL process. 1 times negative 1 is negative 1. Then outer times outer is plus 2i. Inner times inner is minus 2i. And then last times last is going to be positive 2i times positive 2i. That's positive 4i squared. But remember, I squared is equivalent to negative 1. So positive 4 times negative 1 makes negative 4. Now we can combine like terms. So negative 1 and negative 4 together make negative 5. And then positive 2i and negative 2i add up to 0. So we ended up with a real number, and that will go here. So negative 5. Now we add. 4 plus negative 5 is negative 1. Now multiply. 1 plus 2i times negative 1 is going to be negative 1 minus 2i. Just imagine if you multiplied negative 1 times each of these. It's like distributing a negative 1. So both signs are changed. Now we combine like terms. 2 plus negative 1 is positive 1. And then we have our minus 2i. Now we have another multiplication to do. So 1 plus 2i times 1 minus 2i. Let's go through FOIL again. First times first is 1 times 1, so that's 1. Outer times outer made minus 2i. Inner times inner made plus 2i, so those are going to add up to 0. And then last times last is positive 2i times negative 2i, which would be negative 4i squared. But remember that I squared is equal to negative 1, so you really have negative 4 times negative 1, which is positive 4. So now we have 1 plus 4, that's a total of 5, and that goes here. And then add negative 5 plus 5 is 0. Okay, so here's our quotient, but we don't really care about the quotient. All we care about is the remainder. So what we just found out is that f of 1 plus 2i is equal to 0, and that means that yes, 1 plus 2i is a 0 of that function. Okay, here is a practice problem for you. Decide whether 2 is a 0 of f of x. So you know how to do this. I hope you'll pause the video and try it on your own. And now I'm going to go through it with you. So to find out whether 2 is a 0 of this function, we need to go through the synthetic division with 2 in the box and see if our remainder is 0 or not. So my coefficients are going to be 1, negative 3, positive 4, negative 4. So that's x to the third, x squared, x, and then constant. And then I'm trying to determine if 2 is a 0, so I put 2 in the box. All right, now I'll go through the synthetic division process. Pull down, multiply, add, multiply, add, multiply, add. And you can check your multiplying and adding with mine. And now the remainder that we got is 0. So that means that f of 2 equals 0, and that means that 2 is a 0 of f of x. And finally, here is one more practice problem for you that involves a complex number. So I want you to pause the video again and try this on your own and make sure you can do the synthetic division with the imaginary numbers by yourself. And if you've had a chance to do that, now let's do it together. So our coefficients here need to be 1, 3, and 4. We're trying to determine if 2 plus I is a 0, so 2 plus I is what goes in the box. Okay, so pull down. Now multiply. 2 plus I times 1, and that goes here. Now add. 3 plus 2 plus I is 5 plus I. Now multiply 2 plus I times 5 plus I. And we'll need to write that out. When we're showing our work on a quiz, we'll need to write that out because it's not something that happens mentally. So FOIL process, first times first is 10. Outer times outer is 2I. Inner times inner is 5I. And then last times last is plus I squared, but we know I squared is negative 1. Okay, this is going to add up to 9 plus 7I. See, the 10 and the minus 1 make 9. 2I and 5I make 7I. So 9 plus 7I is what goes here. And now we add 4 plus 9 plus 7I adds up to 13 plus 7I. And that is our remainder. So that means that f of 2 plus I is equal to 13 plus 7I. And therefore 2 plus I is not a zero of that function.